Hi, everybody. Mr. Miller here with another edition of TRECAtv. We are joined today by Shane Corbel, who is a software consultant. Shane, why don't you introduce yourself and explain to us what is a software consultant?
Sure. So I'm a digital performance specialist, and I help enable teams build faster applications. So I've been doing this for about 18 months now, and I help companies leverage the best application performance management tools on the market. And I do so by consulting on digital performance, agile delivery techniques, and enabling application teams for various companies to adopt a user experience centered mindset where they're focusing on how fast they can serve up web pages to customers or how they can make their applications faster.
Okay, so for our high school students, let's drop that down a level and say, what is it? So you don't actually produce software. What you do is help make software better. Is that correct?
That's correct. So what I'm doing is I'm taking a kind of like a second set of eyes, so to speak, on a company's application, whether that's something that's delivered over the web, like a website, or whether it's a standalone application, like something you would put on your desktop, like Minecraft.
Okay. And so, do you do phone and tablet based stuff as well, or do you keep it to the keep it to the computer and the web based apps?
It's a wide gamut. It's absolutely everything. So if it can be served up on a phone, a tablet, whether it's Android, iOS, Windows Phone, or Windows desktop-based application, it doesn't matter if it runs on Macintosh or Unix. We monitor it and we can kind of give a second set of eyes and a second look on their applications.
Okay. So, how do you get to be a software consultant? What path in life do you take to kind of get to where you are now?
Well, so it's I don't want to say it's a long path, but it's a very it's a computer focused path, right? I went to school for computer information systems, so I have a background on everything from finite math to communications to programming. Um, I've taken AI courses and advanced data structures and programming classes, and then after I got done with all of that, I entered in a 20-week training program with Dynatrace just to learn their tools. And then after that, I was able to start going to various clients and do my consulting there.
Okay. And so, can you give us a little bit of information about how maybe how you work with? Because I assume this is not a one person thing, right? It's not that you don't go in and say, "Hey, here's this application I want to look at," and then do it all from top to bottom yourself. Do you work
No,
in
no,
teams? How does that work?
yep. So when I come on, it's sort of a long-term engagement. I'm not going into a customer site for a week or a month even. Usually our contracts are for 6 to 12 months, maybe even longer. And what it is, I'm basically a full-time consultant at that company. So I get assigned a team there that I work with, and they help me with all of the various business-related functions, and I help them with all of the Dynatrace related functions. And then when we come together, that's when we can put the stuff to work for their company.
Okay. So, and you said you, and for our viewers, I just want to say, Mr. Corbel is in the process of moving, and he's very graciously agreed to join us. So we do appreciate you. If you're going, hey, that's a lot of cream wall. He's packing up his stuff, and he's literally unpacked stuff so that he can. So we're very very thankful to have you here. Um, when we have a student who is in high school, and they're
Mhm.
looking into the next stage of their life, so a lot of people love computers and they love the idea of either making games or programming or something like this. This is maybe a different side of this. This is sort of a combination of computer knowledge and programming, but also this is very business focused, right?
That's
Uh,
correct.
so maybe kind of taking a step out of what we normally talk about because we do kind of focus a lot on computers and math because I'm a huge nerd and that's what I like, but you have kind of a unique insight into more the business side of things because it's just something that um, that in the education field I don't have any experience with really. So when you're working with what are the traits that make you good at working with and for businesses? Um,
Sure, sure. So there's a bunch of different things you need to be able to do, right? You not only do you have to have a strong science and computer background, but you also have to be very adaptive. I'm getting put into environments where I really have no insight into them before I walk into them, and that's just part of the job. I'm able to quickly take in a lot of information, process it, and then give recommendations based on what I've seen. Um, I'm also one of the traits that you kind of need to be able to do is you're forced to be somewhat of a people person, right? I mean, I'm going to be working every day with companies, and by companies that means teams of people at these companies, and I'm going to be delivering news that might not necessarily be what they want to hear. Nobody wants to be told, where they messed up. So you have to be very tactful in how you approach problems and issues that might come up when you're reviewing somebody else's work.
So I'd love to jump in there because as a teacher, oftentimes my job is to look at someone and say, "Hey, you're not doing this. Well, you think you're doing it the right way, but you're not getting the right answer. Let's take a look at what you're doing." How is that? How do you deliver that news? And is that indicative that they are bad at their job? Is that indicative that they just goofed up in this one place? Can it be both? Um, what does that mean for someone when you're delivering that message? Like, how do they take it? And what is your intent, maybe, to summarize?
Well, the intent's never to be, hurtful or to disrespect somebody or to make them feel belittled. They bring me in when they need to have a job done, and that's what I'm there to do at the end of the day. But it's important to realize that at these are large companies that I'm working with. That there's thousands of developers on these applications, and not every one developer knows what the other one is doing. So most of the time when there's issues that come up, it's because two parts of a program might not have necessarily synced up, or um, they weren't expecting data to be delivered one way and it was actually delivered another way. Or it might be two applications talking together that neither programmer has any knowledge of what the other one does. So it's a lot of interfacing between programs that exposes a lot of risks and a lot of sometimes bad behavior for applications.
So, and this is hard for me because we both been around computers for a long time. So
Hmm.
sometimes we use terms that totally it wouldn't strike me as something that would be difficult to understand. So I do want to kind of talk about how programs interface. So that's
Sure.
something. What do we mean by interface? Because when I'm on Facebook, I have a
Hmm.
user interface. Why is it called a user interface, and what other interfaces are there?
Sure. So there's always like a presentation level interface. Um, this is usually static content like images or links or pictures, stuff that you can click on, stuff that takes you to another page. Um, but all of that stuff comes from somewhere. So that web page that you're seeing is the presentation layer. So let's take Facebook for example, something everybody should be pretty familiar with. Um, you're able to see all your friend information, your own profile, and you can click around and navigate it. But that information is actually stored somewhere, in a database, and then it's served up to you. So how does it get from the presentation layer to the database layer? And that means there's actually an application layer in between. So the web layer talks to the application layer, which talks to the backend, which could be a database. It could be a file system of some sort where it's pulling stuff, information from. There's a variety of different interfaces that all of these things have to talk across. So a lot of it is you can go one of two routes. You can go a common route where the applications have a predetermined language that they're talking to each other on, or you would have a company that might build their own layer to talk between the web and the application, and then the application and the database.
So I think a lot of our students who game or they do things they use web applications. They probably know the word server. They probably know that it means. They may know that it means a computer somewhere else that's providing
Hmm.
information. Um, so let's pretend that they know that, and if they don't, we kind of tell them.
Sure.
Let's talk about database and how it stores information, because this is a total aside, and I apologize for doing this to you, but I think this is kind of interesting since we're in this era of seeing that, oh, this database has been hacked, and all these pictures are out there, or all this personal information gets out there. PlayStation Network, or one of these places that has one of these security breaches. What do we mean by what is a database, and what happens when it gets hacked? What does that mean?
Sure. Now, a database at its core, and there's a lot of different database technologies, so I'll try to keep it pretty high level here. But all a database is it's a place to store information in a way that's logical to find it. So an example of a database might be, you might have a animal database, and in that database you have all different types of animals, and then all of those animals have different attributes. Some might be birds, some might be lizards, some might have 2 legs, 4 legs. Which ones have long necks. All that different information is related to the animal, but they also might share attributes. Like all birds will have feathers, but only some birds might have blue feathers. So the way we put that information into a database and what fields that you're storing is it's all indicative on what you need to know about what you're putting in the database and how it relates.
Thank you. Actually, I really liked that description. That was good. For our students, we're an online school, so students, when you think about it, we have databases of our students. We have databases of our classes and our grades. We have databases of lessons that we keep. Each student entering a database, you have fields for your name and your address and your phone number, who your parents are. You might have links to siblings, so you can link from one element in a database to another element in a database. So that's how we use them at TRECA. And I do appreciate you going into that for us. So basically, here's what I'm hearing. I'm hearing that you work with the team from the actual other business. You don't.
Correct.
And you help them take a look over their work, and then find ways of making their work go faster, smoother, cleaner.
Correct. Yep. So we're always looking for ways that we can help improve the performance, and that can take a couple different, avenues, so to speak. You can have like a response time that you're trying to get down. Nobody likes lag in games, right?
Right.
So when when you click on something in a game, you expect that click to register really quickly. Well, in order for that action to be performed, there's possibly hundreds of different systems that all have to function at the same time. And if there's a slowdown in any one of those, then you're going to get lag, and you're going to see, it's going to make the application feel unresponsive. Going a different route, you might want to reduce the number of back and forth queries that are going from an application to a user. If you have to make a round trip from New York to Florida, you're going to want to do that if you're doing a move, so to speak, you're going to want to make that in as few trips as possible. Otherwise, it's just time consuming. So we might take the look at how can we reduce the number of round trips that this particular application is calling the backend, so that it can serve the same content in less trips.
I like that. Thank you. That's good. Can you maybe tell us a little bit about some of the types of companies you work with? Obviously, you're probably not going to tell us about, oh, I work with these guys and these guys, but can you tell us about maybe the types of companies you've worked with? Do you work with people who do medical services? Do you work with people who do social media? What kind of businesses have you worked with in the past?
Sure. So from a Dynatrace perspective, we have worked with, just an impossible wide gamut of companies. Everything from, like you said, medical to different major airlines to most of the financial sector, insurance companies, credit card processors, just all sorts of different companies that you would think, retail customers, lots and lots of retail customers. So that would be like your an Amazon.com or something like that.
Fair enough. So, I guess my next, I guess as we're talking about these kind of companies that you serve and these sorts of things that you do, um, what happens after you if you do a good job, if you've done the job that you're there to do, right? What is the next step for the company? Are they
So
just happy and done? Are they going on to Amazon 3.0? How does that work?
So the thing about software, right, is it's always in a constant state of iterations. You're always trying to improve while also always trying to add things. So ideally, what I do is I work myself out of a job, right? I'm there to help enable a customer to adopt a mindset where they're focusing on performance and their customers and the user experience that they're providing the customers. So, you know, most of the time when I'm brought in, it's usually to work with a specific application that might be struggling. And after we do that and that's accomplished and we get that performing to where it needs to, it's like, how can we do the next application and how can we do it better and faster? So at the same time, we're putting in a process at the company where they're taking a look iteratively through all of their applications and improving them using our tools.
So let's talk a little bit about the math that you use in your job.
Mhm.
I have kind of a fun, and I'm going to put it up here, a fun example of a Venn diagram that you shared with us. So,
Sure.
what are the types of math that you use at your job? What are the types of things that you do that our algebra students specifically might have to know and understand?
Sure. So we deal a lot with relational algebra. So these are and, or, and not statements. So an and statement is where you have both terms, right? So let's say you're searching for a puppy and a kitten, and you want to see pictures of both. So you want a picture that includes a puppy and a kitten. That would be an example of an and operator. An or operator would be if you're searching for puppies and kittens and you don't care if the picture has a puppy and a kitten in it or both. You want to see both. A not operator is like let's say you want to search for puppy pictures that don't include any kittens. That's an example of a not operator. So a lot of what our software does is it makes these relations between various data sets that we collect, and then we can display things so that we can get this information that might be business relevant to the customer.
Fair enough. Is so most of what you do is relational algebra, and
Correct.
and it's funny because when you look in an algebra one class, that may not be something that people understand is even math, right? They may,
Right.
they may think, oh, that's not math. I don't know what it is. I don't have a label for it, but it's not math.
Yeah.
Um, so can you give us kind of? Are there any other maths that aren't math? That aren't what you'd see. They're not 47 minus 33. What other sorts of math do you use that maybe students don't understand? This actually fits under the domain of math. It's not reading. It's not science. This is a logic field.
Right. So a lot, I'd say probably 90% of what we do is going to be relational like that and use those kind of operators. But we might also use stuff like, break things into percentages. Let's say we have a certain procedure that's happening 90% of the time, and it's causing, only 5% of the total response time. We're going to want to look at that. What's that upper 10% that's causing so much more of the response time, like the 95%. So looking at various percentile data is also another thing that we do. And then a lot of it is measuring response time, which is, how fast can you go from the time you click to the time where the content is served to your web browser or your application, or stuff like that.
And I guess for gamers, you would think of that as lag or okay, pronounce it for me. Latency.
Latency.
Latency. See, I want to do a short A because I'm from West Virginia and we ruin every word that we can say. That's our job. Yeah, so latency or lag, but it's sometimes we think, oh well, we'll reset our router and everything will be fixed, but then you turn everything off, you start everything up, everything every other web page works fine, and then you've got this one thing that you're trying to do. So maybe Corbel Industries, right? So you're clicking on their page, and for some reason their page takes a lot longer to populate to use, and so I guess that would be the situation where you go in and say, okay, where's the hangout?
Sure, and if you want to go to that next picture I gave you, we can kind of walk through it, and I can kind of talk. We can talk about or extrapolate where latency might occur, right? Because it can appear in a lot of different places.
I want to make sure I'm on the right one. It says unknown browser, robot desktop browser.
Yep,
okay.
yep, that's the one.
Okay, we're on it. We got you.
Okay, so in this picture here, this is an example of what you would see in our software, and what it's showing is on the far left hand side there's a user, which is like you, and we're going to maybe through a desktop browser that's going to connect to a web server, which connects to an application server, and then various things on the back end, like maybe an API service from Google Maps or a MySQL server. And that latency can happen anywhere along this entire application delivery chain. So maybe it's your ISP is having problems. So between your desktop browser and the web server, there's a delay there. Maybe some type of static content on the SQL database is hanging up, so it's not able to serve content as quickly, and that's where the latency happens. So there's a lot of different things that can happen when you experience lag or latency. So sometimes resetting your connection just doesn't quite solve the problem. You need to go deeper.
Yeah.
And that's what Dynatrace does with our performance management software, is helps you look into that.
Fair enough. And so I'm gonna throw out a couple questions that I honestly don't know if they're in your wheelhouse. Let's talk kind of a little bit about how the internet actually works for some of our users, because a lot of our students use the internet. They love the internet. That's where you get all your cat pictures, but that doesn't really, there isn't kind of an understanding about how these connections are formed or whatnot. So you type in an address in your browser, and then you pull an actual physical address to go to. Can you tell? Can you tell us a little bit about DNS and how that works?
Sure. So DNS is the domain name system. And what that does is it translates a common name to basically a machine name. So Google.com, that's actually to a computer that doesn't mean anything. It doesn't know how to route that. So what it does is a DNS server will provide back an address, and that's just like a mailing address. Only it's always just a series of numbers. So an example of a web address that gets translated to an IP address, they're called Internet Protocol address, is Google's DNS server. It's 8.8.8.8. That's one of the most common ones you can remember.
Right.
So what your cable modem does is it sees that you want to go to Google. It goes ahead and translates Google into that internet IP address. And then it's going to go through your ISP's network to Google's network. And then that is going to go to a series of computers that's going to actually serve the content. So there's a great number of things in between that desktop browser and the web server that can go wrong. So
does my computer directly connect to Google? Is it just like I send a signal that goes straight there? How does the fact that I want to look up pictures of puppies but not kittens, how does that Google search actually get to Google, right?
Right. So that's going to happen as so Google has their own query system where you put in your query and it somehow relates that back into a database that can serve you all those pictures, right? So if all the stars align and your desktop is able to talk to your router, which is then able to talk to your cable modem, and then your cable modem is able to successfully navigate through your entire ISP or internet service provider's network to Google's internet service provider and network, and then all the way through the reverse on the other end, then you'll actually be able to hit those web servers, and then it'll be able to serve up that content to you.
As kind of an example, our students might understand. Let's talk a little bit about, well, and that you'll understand the basic concept of, but you won't know the specifics of. So we have a content management system, a learning management system. We call this LMS. It's very similar to any generic CMS.
Yep.
And that LMS hosts content from different providers, right?
Yes.
So we have some students who have issues. Okay, here's student A, and student A uses the LMS and gets all of their content really quickly, never has a problem. And here's student B, and student B has a lot of problems, and they're wondering why that could be, right? Are there times when it can be the software on their machine, or is it going to be different steps in between?
Oh, sure. I mean, that could be any number of things. You said it pulls information from multiple different sources, so it could be that student A just didn't have anything hosted somewhere else that was having an issue, but student B did. Or if student B is consistently having issues, it could be something more localized, like a difference in their internet service provider. Student A might be using a cable connection or a fiber connection that's really quick, but student B, if they're accessing things over like an old cable or an old DSL connection or a 56K modem and dial-up, that's going to obviously be a lot slower than the fiber network would be. And then you get into all kinds of issues about the resources on the machine and how fast it's able to actually render, graphics cards, memories, all that kind of stuff that on your local machine that will affect how fast a application or web page can load.
And then taking it from a different perspective, let's say you have two people who have the exact same physical machine. We have several different iterations in play because we have several different generations of students who are going through our system. Some people got their computers at different times. And so let's say they have two students who have the exact same machines with the exact same software. One is in Cleveland, the other one is down in southern Ohio, as an example. How could that look different?
So it's definitely going to look different from an internet service provider's perspective, because even if they have the same service provider, like let's use Comcast for an example. Comcast down in the south is going to be definitely different from Comcast up north, just because it's going to be going through a completely different network. And even though Comcast is the internet service provider for both, Comcast is still going to route their traffic through. So basically, you have a internet service provider called Comcast. Well, Comcast is going to have an internet service provider that they get internet from, basically. So maybe that provider is having a problem in a certain region that's not in another region.
Can you tell me a little bit more about that? Because that's something that might be interesting for our students, that they may never have thought that their ISP has an ISP. What does that mean?
Sure. So what that means is you have a company like Comcast that has their own. It's called a last mile network. So that's the actual cable connection that comes into your home, and that goes to a box somewhere, a Comcast box, that then aggregates all those connections from all the different residences, and that goes to a distribution center. Well, that distribution center might be part of Comcast's own network, or it could be part of they could be contracting that out to a third-party service, or basically a internet service provider of internet service providers. An example, one most people won't be familiar with, is called Level 3. Level 3 is an internet service provider that provides internet service to internet service providers. You can't call Level 3 and ask them to hook up internet at your house, because it would be very cost prohibitive for them to do so.
And so when you have these, and I'm going to head back just one step, which is third-party provider.
Sure.
When we say third party, think of it as in the same thing as like third person. It's not me. It's not you. It's somebody else, right? So
Hmm.
third party
Right.
is that's probably the quickest way I could go through that. So when we talk about cost prohibitive, these guys are not bringing in individual. You're saying these guys are not bringing in individual cable lines.
No, I mean, if we're talking, like, let's say your home internet connection is 20 megs, and then everybody on your block has a 20 meg internet connection through Comcast. Well, Comcast has to be able to serve all of those connections up to a certain point, right? So if there's 100 people on your block, that's 200 megabits per second, or I'm sorry, 2,000 megabits per second.
Yeah, 2000. Okay.
Um, and then there might be multiple blocks, city blocks, and all those get aggregated together. Well, the level three, which is providing internet for Comcast, they're going to be giving Comcast internet connection that's going to be in the gigabit range. Hundreds, maybe thousands of gigabits per second.
So when you say, and so we have bit into megabyte into
Hmm.
gigabyte, and so each one of these is exponential for my students who are in block 11 or who are in block 6. For my other students, what that means is every time you're multiplying it by 1024, not exactly 1,000, but close enough that close enough for government work.
Right.
So when we talk bytes, that is 8 little pieces of data all at once, right?
Yep.
And then when we talk about a megabyte, that's 1024 uh, bits, right?
Correct.
So we go from 8 to 1024, and then 1024 times 1024 is a gig.
Yep.
And then after that, it's what, terabyte?
Terabyte.
Yeah. And
And then petabytes after that.
I'm presuming that we don't have a whole bunch of terabyte service providers.
No, no. Most of those networks are very, very. The number of providers that do that is very small.
And so basically, instead of having to connect, so basically Comcast or generic company C, I don't know.
Yeah.
We probably should have been. I don't know enough about copyright law to know if I'm in trouble at all. So I don't know. I'm sure it's fine. We're talking about how they work. None of this is incorrect. Hopefully.
Yeah.
So company C connects to this high level one, and then how many of these really high level internet providers that provide internet to the like to Comcasts or to the Time Warner cables, right? How many of those internet companies actually exist? Is this a market where you're looking at thousands across the nation? Is this one where you're looking at like 10?
Um,
Is
it's
it
definitely not thousands, and it's probably not in the hundreds even. It's
okay?
it's probably a number lower than 100. And the reason is because these are companies that have very large fiber optic networks that span the country, and there's just not a lot of those, to be honest with you. That's why you can have such widespread outages whenever some kind of natural disaster happens.
That okay? Fair enough. So if you have an earthquake or a tornado that knocks out one of these main fiber lines, then what you're saying is you're not only going to lose Comcast but also Time Warner, also a lot of the internet, all in that large area for the country.
Correct.
Um, is there a way for you to still connect out of that region? Um,
So that's going to depend on how you connect, and who's affected by the outage. Let's say that you know Comcast's network provider got hit by a tornado, so Comcast is out in that region. There's a good chance you'd still be able to connect that on like your cell phone going across, like your Verizon or AT&T or T-Mobile or whatever have you, going across their network, because that's going to be a completely different system. Um,
So I guess as an example for what I was thinking in my head, let's say you're stuck in. So like when I just got married, we were coming out of New York, and our flight to West Virginia got canceled, right?
Hmm.
And our airline was like, we don't fly any other flights into West Virginia. Like, there's no way to get you home. And then what we ended up doing was connecting with a different airline. They put us on a different airline, and then we had to go down to Atlanta, Georgia, and then come back up, right?
Yep.
Is there a situation, and this is, I mean, and I apologize because this is the stuff I'm interested in maybe more than, um, this is what I get for if you want better questions, submit better questions. Um, yeah, submit some math questions, guys. Let's say that you have one of these really um, high speed connections between, let's say, LA and New York, okay?
Yep.
And let's say you have another one between LA and um, Austin, Texas. I don't know what else
Hmm.
would be another, and then Austin. So and then Austin connects through Atlanta because we already said it, and then Atlanta goes up to New York, right?
Yep.
Would it be possible? Let's say that we have a tornado, or a pipeline burst or something like that, or whatever natural disaster you need, and New York can no longer talk to LA, right? So that
Yep.
line is broken. Could LA reroute? Would the internet service provider be able to reroute traffic through Austin and then back up on the eastern board through Georgia, or would that connection just stop existing?
No. So the that's a really great example to show how the internet actually does work because um, all of these devices are interconnected in such a way that they're going to start taking the shortest path available to them. So if one path goes down, it's going to suddenly reroute over another one. The issues with that, of course, though, is that number one, it takes time for the devices to reroute because when we're talking about major internet lines, a lot of these are set to have a pretty high degree of tolerance if it goes a little bit shaky for a while because rerouting a major traffic line is not an easy thing to do. Just like a major airline wouldn't be able to do it right away. So you're gonna have to bring all these planes and reroute them to, I think you said Houston, Texas. Um, so rerouting all those flights that were originally going from LA to New York to Houston, Texas is going to put congestion now on Houston, Texas. And then all of those planes are then going to have to get rerouted back over to New York. So because of the network congestion in Houston, you're going to see delayed flights, higher latency for everybody as you're trying to put more traffic over that location than was originally intended.
So that might be an example of why, um, even if we don't have snow here during a major blizzard, our internet might slow down. As an example.
Right,
Cool.
right, exactly.
Um, so, and at some point, I need to break in and do. I have a couple students ask who want to know about a math question, but I do want to talk a little bit about the way that um, routing affects students specifically because it is something that has come up for us before, right?
Hmm.
Students in an area, we actually provide service to our students through cell phones, and we
Yeah.
have two. We've recently picked up a second cell phone provider,
Hmm.
so that if a student doesn't have internet access in their home or their home is slow or whatever for whatever reason, students basically use cell phone hotspots to provide
Yep.
internet access.
Yep.
So there have been a lot of students who are saying, "Oh wait, my internet has not been good through TRECAtv for a long time," and then we picked up a second carrier, and then suddenly some of these students could trade in a phone, and suddenly their service actually worked much better, right?
Hmm.
So
Yeah.
why would that be the case for some of our students who are especially outside of the major cities? Why would that be so helpful?
Sure. I mean, when we're talking cell phone providers, all of that, all cell phone providers rely on, wireless signals. That's the whole concept of their technology, right? So you're at the mercy of, radio waves. And the interesting thing about radio waves is that they behave very differently in different situations. And what I mean by that is you might have one provider that's on a cell phone tower just a mile away from another one, But because of the different buildings or trees or whatnot that gets in the way, the signal strength for the other one is going to be significantly higher where you're located than the other. This is how dropped calls happen. This is how, in some areas you only get 3G versus, the edge network or, any of these various cell phone technologies. It's highly dependent on signal strength for how high a quality of a connection you have. And the higher quality of the connection, the more reliable and the faster it's going to be. Sure. I don't. Yeah, absolutely.
My
So we
microphone was
use.
muted through all that. My students heard none of that. Since the last time you
Oh,
talked, students have not heard a word I've said. So, hey guys,
oh,
I'm kind of a dummy. Um, so, crap. I'm going to walk back. Well, you work out some of these glitches. I'm going to walk back and kind of talk. I'm sorry.
you're fine.
So, yeah. So, when we talk about, a lot of students have been having questions about point slope form and slope intercept form and when to use what. So, what I was saying is that slope intercept form looks like y equals mx plus b, and point slope form is y. See, I'm all red now. This is embarrassing. Equals m times the quantity x minus a. And these formulas look pretty different, right? But the thing is that these both represent a line. The thing is that the slope intercept form, y equals mx plus b, is specifically when one of your points is on the y-intercept. And when the point is on the y-intercept, that means that x has to equal what? right? It has to equal 0. So that means that we have y minus b equals m times x minus a. And when a equals 0, we end up with y equals x minus 0. X minus 0 is the same thing as x. M times x is mx. We have y minus b equals mx. And then if you add b to both sides, you get y equals mx plus b. So these are not different equations. Y equals mx plus b, slope-intercept form, that is just a specialty case of point-slope form when the point that you're using happens to be on the y-intercept. Happens to be the y-intercept. And it's super nice and it's super easy because it takes away the subtraction and it makes it addition. Which I think is the real benefit of this. It feels clearer. When you say it has a slope of 3, you know it's going to go up 3 over 1, and you know it's going to cross at 10, right? That's really easy in your head to figure out what that's going to look like. Oh, that's going to go through here, and then that's going to go through here, and then that's going to go through here. So that my line's going to look kind of like that, right? The benefit of this is that it feels clearer. The benefit of point-slope form is that any slope that you use, any point that you use, you can find an intercept for it. You can find an equation for it. So that is what I was telling you, but was not telling you. That was the pretend hidden message there. It wasn't maybe as earth-shatteringly mind-blowing as maybe you'd wanted it to be. So we're about 8 o'clock. We'll do about 15 more minutes, and then we'll wrap up. So once again, I really do appreciate you being here. I know that it's kind of a pain in the behind to stop moving to do this, so we are really grateful. You're moving up our way, aren't you?
Yes, I'm actually moving to Ohio. I'm moving to Cincinnati.
So yeah, so you'll be in our radius now. You can now be one of our students.
Oh,
Yeah, probably
nice.
Won't be necessary, but
going back to your question though, you asked prior to that is, I don't do a lot of slope-intercept graphs, but I do a lot of visual representations of data, that's all a graph really is, right? So if you want to go to that next screenshot I had sent you.
see, look how convenient that is.
I know, right? We didn't plan this at all. We swear.
He gave me a Word document. I honestly, for the record, I have not looked through all the slides yet, so I hope there's
Perfect.
nothing bad in this that I'm not supposed to be showing.
No.
Okay.
So,
I'll
so at the top there, or in the middle, I guess you can kind of see a breakdown. It's a graph, right? It says CPU and it says I/O, and you can't read the yellow one, but if you could, it would say suspension time. And without going into any great detail about what those are, what that's just doing is giving you a quick breakdown of which percentage of this transaction was in each of these categories. And then if you go into the bottom half of that screenshot, you'll see a similar breakdown of which percentage of that transaction was of what type.
And I love the word transaction, and you use it in a much more general form than when we think of a transaction. Often we think of, okay, you give me a good, I give you money, I pay for it, I get a receipt.
Right.
That's a transaction.
Right.
In a much more general form, what is a transaction that we're talking about here?
So when I talk about a transaction, what I'm talking about is when you click on login after you type in your username and password, and then that's a transaction. What needs to happen to let you log into an application or let you log into a program? That's what I'm talking about when I talk about transaction. Clicking on checkout when you're at a shopping application, that's a transaction. Adding stuff to a cart, that's a transaction. So basically every action relates in some way to a transaction of some sort.
So every action that has a computer-based reaction is a transaction.
Correct.
Okay, I got you. So now, for instance, in this one it says synchronous invocation, and then web request, blah, 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 exception, exception, exception.
Yep.
Is this all a single interaction that you're following?
Correct. So this when you click on login, it's going to give you a breakdown of how that login request went through their application delivery chain, and it's going to give you a breakdown on how it does so. A transaction might have, maybe a short, 10, 15 type things on the back end that you might see in this list. Otherwise, it could be hundreds, maybe even thousands of different things that make that transaction happen. It's all going to vary based on what that particular transaction does.
And so each of these could be. It seems like each of these could be a different server. They could be a different piece of software. They could be, any number of things. And so when you have a company that's working on the internet, that's doing these sorts of things, this is like the reason that we do group projects right here, right? Like this is why you have to work with Timmy and Sarah, and you're sharing a grade.
Yep.
And I will tell you, college students hate nothing more than group projects.
Yes, yes, and those are often the best examples I've come to see of, when you get put into a large corporation and you are working on a project together. That's often how they go. Everybody brings their own attitude and diversity and ideas, but you have to come up with a common directive for your application in order to make it behave cohesively. You can't have everybody working off on their own, and you can't have one person building the entire thing. It just doesn't work out as you would expect.
Cool. Okay, so I feel a little less bad about the number of group projects I've done in the past. I don't currently have any in online algebra,
Mm-hmm.
but yeah, Mr. W and I are talking. So, if you don't want them, you should probably work quick and get through things, guys. Because if you're slow, you get to block 9 or block 10. If you got a group project, you got a group project. Just try to get through.
Yep.
Go ahead.
Oh, I was going to say I have one more. The next screenshot I have on there is a chart of just a single response time graph. It's just of a random DNS time. So would be an example of another type of graph I would use, where you'd see how your DNS speed might be at one point in time and how it varied. If there was maybe something that a code deployment that happened, or maybe there was a problem upstream on your provider, we'd be able to see the response time difference and when it occurred, and then be able to relate that back to an event.
That's cool. So when we're looking at these sorts of things, what it looks like Mr. Corbel uses is, when you look at our data, we have a large section in algebra that deals with data. We're looking at box and whisker plots. We're looking at all these different ways of categorizing data. What is the 25th percentile? What is the 75th percentile? Those are the skills that you will really want to have mastered if you are looking at going into an industry where your job is to figure out how to make somebody's experience better on average. You want to look at what does good look like, what does bad look like, and how often do they happen? When do they happen? You're gonna line some of these events up, and you're gonna use that data to do so. So I really appreciate you bringing these examples, because this is very similar to a large portion of what our course does. And so it's nice to see it actually in play, making things better.
Yeah, and that actually brings me to my last screenshot I sent you, where when you're talking about a user's experience on average, and just very briefly, what this screenshot is showing is, database calls, how many times they happened, what's the execution time average versus the execution time minimum and maximum. And when you're trying to improve something on an average, you might have a database execution that took, let's say 2 seconds, that's really a long time in terms of getting stuff back from a database. But if it only happens 2 times, that might not necessarily be something you want to focus in on unless it causes a transaction to fail. But if you have something that happens, 100,000 times, and the execution time is 20 milliseconds, if you can get that down to 15 milliseconds, you're going to improve the average response time of your application a lot more than if you went back and fixed that 2-second transaction that happened only 2 times. And so you have to look at you have to look at the data set and make, where am I going to gain the most here? Do I need to focus on reliability, or do I need to focus on, just bringing the total response time down?
So if you're working for a company and your company has 1,000 workers and your job is to make the most of those 1,000 employees, then bringing the average response time down makes a lot of sense. Because even though some people may still be waiting at their keyboards for a little bit, everybody gets more work done on average, right? So
Correct.
that may make more sense for you if you are an ISP or one of these other companies where if you're waiting for 10 seconds for something to load, they're going to feel like this is a real problem and that's going to make customers angry. Maybe it's not the average that you really need to bring down. Maybe it's these maximums that are the biggest issue.
Right. I think, a heavy transaction-based data source, like maybe a credit card processor. So when you swipe your credit card, you want that to happen pretty much instantly. Now, somebody like, a web retailer like Amazon, they would want to make sure that when you click on checkout, every checkout occurs, even if it takes a little bit longer. If you're having a failure happen at checkout, that could be a potential lost sale.
Right. That's I appreciate that. That's a wonderful example. And so I really love this, by the way, because this is when we're looking at data. When you're looking at your box and whisker plots, this is your leftmost tick, right? This is the very end of your chart. This is the average is you have the box and then there's a line in the middle. That's this. And then this is your rightmost mark. And then when you put all these together, when you look at every single example, that gives your total, and then you can look at your number of executions. And my guess is, divide this by this, you're going to get your average. So when we talk about execution max, can I just take a look at some of the data? This is actually interesting. This one has 153,000 millisecond as its maximum.
Mm-hmm.
That's, in computer terms, that's a long time. Now,
yeah, it's forever.
Students need to know a millisecond is 1,000th of a second, right?
Right. So 1,000 ms is 1 second.
So this took, 153 seconds? 2 minutes, 2.5 minutes?
What are you looking at?
The very top execution.
So the top is the aggregation of everything below. I should have pointed that out. But you can see that little echelon. If you collapse it, that's going to be your total.
I feel
everything below it is added up at the top, and then it kind of expands. So really, line 2 is where you're going to start seeing the individual queries.
It's good to know. I feel.
Yeah. Sorry.
No, that's good to know. That is another aggregate piece of data, and you need to understand how your data works to be able to manipulate it. So the longest transaction time we have then is 2.5 seconds, 2.7 seconds, looks like, from the top group. And that's yeah. And so this it's 2,700, but that means 2.7 seconds. But the thing is that 2.7 seconds in terms of computing, that is slow, right? That is not a good response time.
But if you look at the average, though, the average is still quite good.
Yeah. And so this would be one of those examples.
It's an example of an outlier.
Yeah. Yeah. Okay. So I really appreciate you coming by and talking with us. Is there anything else that we didn't hit on that you want to talk about? Is there anything else that you want to mention?
Nope. If you have any questions from students, please feel free to either ask them now or forward them on to me. I'd be very happy to answer them.
Okay. So if you have any students, if you have any questions, not if you have any students, that'd be weird. Students probably should not have students until they get. There's like a big long process, guys. But if you have any questions, you can tweet them at TRECAtv. You can email them if you are in Brightspace, mamiller@tda.com. If you are off Brightspace, mamiller@metasolutions.net. And I will get those forwarded along, and we'll get you some answers. Thank you so much for being here. I really appreciate you coming out, even in the process of moving. So
it was my pleasure.
Thank you for joining us. I am actually going to drop into, and I'm going to show you, we have been working a little bit on TRECA Studios. And Shane, if you would like to continue to join us, you can. If you would like to enjoy the rest of your evening, you can feel free to do either way. I am going to bring us up into We have been building a TV studio in Minecraft, a TV, TV studio, and I wanted to kind of bring us along and update us as to what we're doing. And we've actually started a second building. For those folks who haven't joined us since the beginning of the creation, would you? So, Shane, have a wonderful rest of your day. I won't make you sit here and listen to me talk about Minecraft. But if you want to join us, you can view it on stream and then send out any messages you have. So thank you so much for being here.
Sure. Thank you.
Take care. Okay. So we are in TRECAtv Tower. This is the CEO office, which I have claimed as my own because I built it. Each light switch controls individual lights. Executive boardroom. We have a seating area up here and a little receptionist desk. And then this is suite 601. So there are 6 floors in this building. Each of the stairwells has light. This is for those folks who didn't watch episode 0 because it wasn't really an official episode. This is our TV studio. It's got a couple of bedrooms for our little, I guess, sitcom or drama here, living room and kitchen. Each of these are equipped with stage lights. So if you hit that, it'll turn on the stage lights over top in order to provide light while you're filming. So, and then as we go down, we find ourselves in executive offices. Dr. Bailey joined us last week. Turn on the overheads. Dr. Bailey joined us last week. And so she has made her office here. We'll find out if Mr. Corbel plays Minecraft, and if he does, he can make an office in our building here. It's kind of a thank you. It's kind of a permanent memorial to joining us in Season 1 of TRECAtv. Studio 3A is for our talk show. So here's the audience. You can sit and watch. Doesn't do you much good, though, with the lights off. So, lights for inside the production booth. And house lights. And stage lights. So you can watch them produce their talk show. Now, this is not actually the only studio on this floor. Oh, and this goes to the backstage area. Everything has its own circuitry because I spend too much time on things. Each of the guests has a little dressing room. You probably should not feel super comfortable with dressing in this dressing room, honestly. You should probably already be dressed and just use that to, like, get ready for your show. Turn the lights off. We're saving electricity, people. Be responsible. And then this is our newsroom. We have a whole bunch of cubicles set up. We have no one in the cubicles yet. So this will be our second round of people who help us with the show after the first generation. This is our control room. Lights for the control room on the far side because that's the best place for them. It's not, it's the worst, but I had to get the circuitry in, so there we are. Okay. And then, so from the control room, you can flip on this light, and our green screen panel gets stage lights. This light lights up our news panel, and then on the right, this lines up our news desk. So we have our map for weather, and that's interesting. So we've carved out a lot of things over here, and so we'll need to go back in and take new map pictures. And then this is our little news desk here. Okay, so that is our news room. Boom, boom. I know, right? Why are we shutting off all the lights? It's pretend electricity. But it matters. Ladies and gentlemen, it matters. Every little bit. Okay, and this was the part that's new for us. This is the lobby area. Previously it was unfinished, now it is finished. So we have an area over here. You can either continue going down or you can go across. We have a fountain that goes down here. And this is our lobby. We have artwork here. We have a gift shop on this side, so if you want to buy a Treca pretend branded t-shirt or hat or some gift, they're here. That will go down to a waterway that's not actually made yet. And you'll see there are lots of seating areas, including these benches by an indoor tree. If you remember, if you've seen it before, you know that we have a nice fountain outside. We have actually brung the circuitry for the fountain all the way over to here. So if you flip that switch, then the lights on the fountain and the water will turn off. We're going to clear up the weather. I don't want to walk around in the rain. So we're going to turn our fountain back on. We're going to go outside. And we're going to make it dawn. Okay. So what we've been working on, and I wanted to show it to you now because it's in a very particular state. We're starting to carve out a road. Dr. Bailey is helping me here. She has carved out, this used to be literally a mountain, and now it is the first floor of our, this is going to be our math museum. So I'm going to fly up, and you're going to see this is not in any way done, right? This is not done. It's not finished, but I wanted to show you for a couple of reasons. The first of which is that when you see me go in and flip a light switch, I want to show you kind of what that process is, right? Why it's every light works. So for this particular light switch, you'll see lights up all the way around the room, boom, down the ceiling. What that means is that we've got circuits that go through every single wall and then up in the middle of them, right? If you go over here and you look, this, when we flip the light switch, that either activates or deactivates a circuit down there. And then that circuit goes all the way around, lighting up or not lighting up. And then like this, it travels upwards like this to get to the wall lights. So each one of these is done with lights that go through the wall. This is the only room that is finished. This is the Boolean logic room. And it's actually pretty funny that Mr. Corbel was talking about that stuff today. And this is, when we get done, you'll be able to see this and walk through this part of it to kind of see how the wiring works. But it'll be closed off so you can't go through all of it and get lost. For the circuitry, I've also put in this so that if you hit the button, it shows the circuitry. And that is done with command blocks, if you're familiar with the game. That swaps these for brown glass and then swaps them back. So I wanted to take a look a little bit at the Boolean logic because he had mentioned and or yes, like exclusive ors, which he called nots. You know, this, not that. So this is a basic circuit. The light is off, but when you power the input, the output goes on, right? That's a basic circuit. If the input is on, the output is on. This is a NOT gate. Okay, it's also called an inverter. If the input is off, the output is on. If the input is on, the output is off. Whatever this is, the output's doing the opposite. Okay, so this is called a NOT gate. It's commonly called an inverter. And this is the last gate that Minecraft specifically has built in, which is the OR. If circuit A is on, then the light is on. If circuit B is on, the gate is on. And if both are on, then it's on. So if either A or B or both are on, then the output is on. But if neither are on, the output is off. So either A or B can power the output. Okay? These are the only two things, and if you notice, you just connect the circuits. And in this one, you light a torch, and then the torch, if you light the torch, it turns off to invert. These are the only two circuits that Minecraft has built in, not and or. But with those two logic circuits, you can build everything else. And is a fun example. Okay? And is really hard to build. What that means is, if one is on, the output is off. If the other one is on, the output is off. If both are off, the output is off. But only if this and this are on is the output on. The thing is, there is no AND gate, right? So the way this works is we invert the signal. So this says if this one is off, then it's on. If this one is off, then it's on. Okay? So these are active if either of them are off. So if either of them are off, this is activated. This says if the previous signal is not on. So it says if either of these are off, then turn this off. So it uses inverters in the OR gate. This is NOR. What that means is if nothing is on, that's on. If one is on, it doesn't matter which one, then that's off. If both are on, that's off. So what it says is our output is only on if neither this nor that is on, right? And nor is a word that we hear a lot. We hear and, or, nor with neither nor. But here's one we don't hear a lot, NAND. NAND. And NAND is not AND. So that means if nothing is on, it's on. If one is on, it's on. If the other is on, it's on. But if both are on, then it's off. So it's not AND. It is the opposite of AND. So this says if this side is off or this side is off, then this gets powered. It's a pretty easy circuit to make. Last but not least, we have my personal favorite, which is exclusive OR. And you'll see XOR, XOR, I don't know how you pronounce it. I always said XOR when I was programming. So exclusive OR is cool. Because the only way that exclusive OR works, if both are off, then it's off. If both are on, then it's off. But if just one is on, then it's on. And what's cool about this is there is a very specific, you have to partner OR. So this is you invert, so you say if not A or not B. So basically it says if A and B, then power this one. Okay? If A and B, power this one. And this one says if not this one, if not this one. So, and then those get inverted. And if one is lit, then we end up lighting the output. It's actually a pretty cool circuit. So that's my favorite. That's exclusive OR. So this is the first room in our math museum. It is dedicated to Boolean logic, to ands, ors, nots. And I'm really glad that Mr. Corbel brought up that this is math, because it makes I'm glad that we walked in and had that example first before we put it in the math museum. So this is what I'm working on. I wanted to show you kind of how the building works, how much time goes into each room when you think about literally how many offices and how many buildings are in our original TV studio. That each one, maybe it doesn't take this much. This is more than what we've done in the other one, but it takes a similar level of circuitry to make each of those rooms work, and each of those rooms is on an independent circuit. So, just to kind of give you an example of the time that we're putting in, I wanted to show it to you. And then this will open up into a street here, which we're carving out of a wall currently. So that's where we are with the Math Museum. Last but not least, how we're labeling the Math Museum, plus, minus, times, divide. Yeah. Addition, subtraction, multiplication, and division on both sides. So this is our Math Museum. It is a work in progress, and I will keep you updated as to how we progress. So one last time, I want to give a huge thank you to Shane for joining us in the middle of a move. I know that is not a fun way to be brought into something. So I'm incredibly appreciative of you doing that. Oh, and last in the lobby of our original thing is a coffee shop here. So if you need a coffee and you work at TRECAtv, come over and hang out here. Okay. So that's going to be the end of our broadcast for this week. Thank you so much for tuning in. We will not have a broadcast next week because of the holiday break, but I believe that when we come back the week after that, we will be having a city councilor from Virginia join us. So if you have any questions about math and politics, or city level, what city level politicians do, or how they try to make towns better, then please send those to us. You can send them to me. You can send them to Mr. Daly. I'm sure he'll send them our way. So thank you for tuning in. Thank you one more time to Shane Corbel for joining us. And have an awesome rest of your week, everybody.